The Euler characteristic is a classical invariant, and usually it's treated rather early in a course. We're rather late in the game introducing the Euler characteristic, but we're now in a position that we can prove all the theorems easily. The Euler characteristic is defined as an alternating sum and we introduce the Euler characteristic for a finite CW complex. Yeah, it's defined as the alternating sum of the number of p cells. We have a finite CW complex, so we have finitely many cells in each dimension. Therefore, this is indeed a finite sum. The definition is dependent a priori from the CW complex structure. So it's, as we define it, it's not just an invariant of a space, of a topological space X, but it's really, first of all, an invariant of the CW complex structure of X, and we will see to what extent this definition depends on it. Historically, was this Euler characteristic first studied for graphs, and there is a famous theorem by Euler describing planar graphs and giving a formula for planar graphs. So what is a planar graph? A planar graph is a graph that you can draw in the plane such that the edges only intersect in the vertices. So for a finite planar graph with v many vertices, E edges, and F faces. So the planar graph partitions the plane into areas. One of them will be infinite, and these are called the faces. And we have the famous Euler formula that V minus E plus F is equal to 2. So that was the first instance of an Euler characteristic. And why is it an Euler characteristic? So how do we interpret this formula as an Euler characteristic? We need a finite CW complex. What is the CW complex? So this is drawn in a plane. The plane is not compact, it's not finite in any sense, but we can compactify the plane. So we can take the one-point compactification of the plane and therefore obtain a sphere. And this finite planar graph can be seen as the von skeleton of a CW structure of the sphere. And the faces become the two cells. So let's draw a little picture. So here is an easy planar graph, nothing complicated. In that picture, the number of vertices is 4. The number of edges is 5. And the number of faces is not 2, it is 3, because we have these two finite faces, but you always have to count the infinite face here that's outside of the graph. And now we want to consider this on a plane, so on a sphere. So we take the one-point compactification of this picture by stereographic projection. You can now project this graph onto the sphere, and then we obtain the corresponding picture. Okay. Morally, something like that, drawn onto the sphere. And then we have a CW structure with this one skeleton, and then we have 3 2 cells, and what was formerly the infinite 2 phase is now, well, the back of the sphere, and the attaching map for the 2 cell that belongs to this infinite phase is just the map from S1 to the sphere that goes around this, like that. That's the attaching map of the 2 cell associated with the infinite phase.
May I just ask, in what sense is a single point not a planar graph? What condition of the definition rules that out?
If you have a single point, you have one infinite phase. So you have, in this formula, you have 1 minus 0 plus 1 is 2. The formula is still true. And the CW structure on this 2 sphere that you get in this extreme case, where you have just one single vertex and no edges, is actually the easiest CW structure that we already considered, where you have a 2 cell that is just, the attaching map is just the collapse map to the point.
Right. And then the formula also works. You have one V and one F and no E, so it's 2. Yes. Okay, no, never mind. So a point is a planar graph.
Yeah, if you want, yeah. Well, check this formula if you want for a specific planar graph, maybe for the one that you just mentioned, where you just have one point, where it is true. And then you want to know it for all planar graphs, and one thing that you could do is actually to prove that the Euler characteristic of a CW structure of the 2 sphere does not depend on the CW structure, because for that specific CW structure that we had, this sum is just 0 cells, number of 0 cells minus number of 1 cells plus the number of 2 cells. So this is the Euler characteristic of this structure. And now you want to prove that this is really independent, this Euler characteristic of the chosen CW structure of S2. So you really want to prove that it is an invariant of the topological space S2, and then you could prove Euler's formula. We'll do this in greater generality, not just for this situation of planar graphs, but it will be a consequence of the more general statement. And to formulate it, I want to introduce the notion of Betti number. So the pth Betti number and now I allow arbitrary topological spaces, not just CW complexes. Is defined as, we look at the singular homology group. To emphasize this, let me write it out. HP singular of X. This is an abelian group, and we can take the rank of this abelian group. So let me write RKC for the rank of this abelian group. So this is either an integer. If the group is not finitely generated, then the rank is infinite. So this rank, you could also interpret this as a vector space dimension. This is the same as taking the Q vector space dimension of HP singular tensor Q. That's the same. Actually, I will most often drop this brackets here. And this is also the same as taking the dimension of singular homology with coefficients in Q. Right, the difference between the two is, so here you look at the cellular chain complex and rationalize it. So you tensor it with Q, or you just, if you don't like the tensor product, you just take Q linear combinations of singular simplices, and then take the homology, and here you take first the homology, and then you tensor with Q, and the two are isomorphic because tensoring with Q is flat. So if you have a short exact sequence of abelian groups and you tensor it with Q, it stays a short exact sequence, and therefore they are canonically isomorphic, and therefore you can interpret this as a Q vector space dimension. Now the theorem that allows us to conclude that the Euler characteristic of a CW complex is really an invariant of the topological space is the Euler-Poincaré formula. And it says that for a finite CW complex, the Euler characteristic of X is the same as the alternating sum of the Betti numbers. On the right-hand side, this is an invariant of the homology, and therefore really an invariant, topological invariant of the space. Even more than that, homology is a homotopy invariant. So from that formula, we immediately get the consequence that the Euler characteristic is a homotopy invariant. So before jumping into the proof, let's first discuss why this formula makes sense at all. The Betti numbers are in that case finite numbers, therefore it makes sense to take an alternating sum. Why is that? Well, the Betti number is the rank of the singular homology group. The singular homology of a CW complex can be computed from the cellular chain complex. Since this is a finite CW complex, the cellular chain complex consists of finitely generated abelian groups. Therefore, also the homology of that complex is a finitely generated abelian group and has finite rank. So all these numbers are finite and the sum makes sense. It also stops at some point because beyond the dimension of the CW complex, the cellular chain complex is 0, and therefore, as we've seen before, the singular homology is 0. So it also is a finite sum of finite numbers. We want to prove this theorem now by basically a technique called homological algebra, something that we will go into at a much deeper level later. So it's basically an algebraic manipulation of chain complexes that we have to do. The chain complex I want to manipulate is the cellular chain complex of my space. Let's just abbreviate this with C star. And note that the number of P cells that appears in the definition of the Euler characteristic, this is just the rank of CP. Because the cellular chain complex in degree P is the free abelian group on the cells, on the P cells, and therefore its rank is just the number of P cells. Therefore, we can rewrite the equality that we want to show as the alternating sum of the ranks of C star on the one side, on the left side, and on the right-hand side was the alternating sum of the Betti numbers, but the singular homology is the homology of the cellular chain complex. It's the homology of the complex C star, and the Betti numbers are the ranks of these groups. So here we have the ranks of the homology of C star alternating sum over P. So this is what we have to show to prove the Euler-Poincaré formula. And this is now just a statement about chain complexes of abelian groups. The topology is gone. The proof relies on two short exact sequences, or two families of short exact sequences. The first short exact sequence is just the statement that homology is a quotient of cycles by boundaries. And therefore we have a short exact sequence of the P boundaries inside the P cycles. And then we have homology as a quotient of that. Okay, so let me, as a remark here, these are the boundaries. So this is the image of the boundary. Now I'm always confused whether I have to write P or P plus 1. I think P plus 1 in our conventions. And these are the cycles, so the kernel of the differential. And the second short exact sequence, or type of short exact sequence, is the fact that, what I just said here, that the cycles are the kernel of the differential. So here I want to consider the differential. So that would be the differential in C star, so in the cellular chain complex. The image is BP minus 1. And the kernel of the differential consists of the cycles. So that's the second type of short exact sequence. All right. Now, the important fact that we have to use is that the rank of an abelian group is additive for short exact sequences. So additive means that if you take the rank of the middle term, then it is the sum of the ranks of the two outer terms. And that's a property that you hopefully know for the rank, and if you don't, you surely know it for the vector space dimension. Because that's the dimension formula in linear algebra, that if these are Q vector spaces, then the dimension of the two outer terms equals the dimension of the inner term. Okay, so let's start with the left-hand side of the equation we wanted to prove, which is the alternating sum of the CPs. So the rank of CP is here the sum of the ranks of these two terms. Now we go into the first sequence. Let's have a look again, where we can express the rank of the P cycles as the sum of the ranks of the P boundaries and the homology. So here I have the rank of BP plus the rank of HP C star plus the rank of BP minus 1. And now we're almost done, because you see now that you have here the rank of BP minus 1, but in the next summand, this term will appear again here, but with a different sign. So all the ranks of the boundaries cancel each other. They're cancelled by the next one. And what's left is just the alternating sum of the ranks of the homology. Which is exactly what we wanted to show, that these two terms are the same. So just for your amusement, I want to make a small remark here. I said before that from the Euler-Poincare formula, we immediately see that the Euler characteristic is a homotopy invariant. And the fact that it's a homotopy invariant can be exploited to solve combinatorial problems, which is very nice. So let's look at a space with a very complicated CW structure, but with a very easy homotopy type, the standard simplex. So that's just a triangle for n equals 2 and a tetrahedron for n equals 3. And the standard triangulation of delta n has the property that the p cells, so the p simplices if you want, but as a CW structure, the p cells are given by collections of p plus 1 points. So for every collection of p plus 1 points in the whole set of all vertices of n plus 1 vertices, you obtain a p cell. And therefore, the number of these cells is a binomial coefficient. So we get a complicated sum here. So again, for the number of p cells, we choose an arbitrary subset of p plus 1 vertices among all vertices, and there are n plus 1 vertices. On the other hand, delta n surely is contractible, so this is the same as the Euler characteristic of a point. Euler characteristic of a point is just 1. So you obtain this nice combinatorial formula, and there are other combinatorial formulas that you can obtain from similar considerations, actually a part of combinatorics that uses topology as a tool.
Yeah, and actually it's also, it can also be employed the other way around. For example, if you have a complicated CW complex, it might be difficult to see whether it's contractible or not. And as a first test, you can compute the Euler characteristic by just counting cells and taking this alternating sum. And if you don't get 1, then you're done. Then you know it's not contractible.
Yeah, and that's an advantage of the Euler characteristic as opposed to homology, that you immediately see, given the CW structure, its value. You don't have to compute anything, just count. And if your CW structure is given, you're right, this is the first test. Okay, so I want to discuss some further properties of the Euler characteristic. The first one I will not prove. There is a product formula. So the Euler characteristic of the product of two finite CW complexes is just the product of the Euler characteristics. And this can be seen by taking a suitable CW structure on the product. Then it's quite immediate. It can also be seen from the Euler-Poincare formula when we think of the Euler characteristic as the alternating sum of the Betti numbers, but then it's a bit harder and probably will be discussed later in the course. Either way, don't want to prove it now, but we have this formula. And we have something called additivity formula, which is a statement about push-outs. So let A, X, and Y be finite CW complexes. And let the following diagram be a push-out. Where here we have a closed neighborhood deformation retract. Then the space that we obtain from the push-out has the homotopy type of a finite CW complex. And the Euler characteristic of this space is the sum of the Euler characteristics of X and Y minus the Euler characteristic of A. Okay, so why this complicated statement? Well, if I would assume that F is a cellular map and A is not just any closed neighborhood deformation retract into X, but it is the inclusion of a subcomplex, then something that I don't think we discussed in the course so far, but then you can give a C the structure of a CW complex, and actually there's a unique CW complex structure on C such that this inclusion that we get automatically is an inclusion of a subspace. And the P cells of that CW structure
Of a subcomplex, you mean, right?
this is then the inclusion of a subcomplex.
Yes.
Yeah. And the P cells of C are just the P cells of Y and the P cells of X that do not appear in A. And then it's immediate from the definition. So what I formulated here is more general, so the push-out is more general. I don't assume that F is a cellular map. I don't assume that A into X is an inclusion of a subspace. And then you can still show by something called cellular approximation and some other tools that the resulting space is homotopic to a finite CW complex. And from the Euler-Poincaré formula, we've seen that if we have the definition of Euler characteristic for finite CW complexes, we can immediately extend it to spaces that are homotopy equivalent to finite CW complexes. So in that sense, Euler characteristic as an alternating sum of the Betti numbers, this chi of C makes sense, and then we have this formula. And sometimes people say that the Euler characteristic behaves like a measure. And indeed, if you think of the case where F is also an inclusion, then X and Y include into C, and this subspace A is really just the intersection of X and Y within C. And then this property that you see here is that the Euler characteristic of the total space is the Euler characteristic of X and Y minus the Euler characteristic of the intersection. And this is the property that a measure on the space C would have. Of course, it's a bit different here. This Euler characteristic can be negative, so it's more like a signed measure. But sometimes you see this phrase that it's like a signed measure, this additivity property. So let's prove this additivity formula using the definition or the characterization, I should say, of the Euler characteristic as the alternating sum of the Betti numbers. And for that, I consider the Meyer-Vietoris sequence of this push-out. We do have it because we assumed a closed neighborhood deformation retract on the left vertical map. So let me draw here the end of the Meyer-Vietoris sequence. Okay, so now comes an algebraic trick. This is a long exact sequence but I want to consider this as a as a chain complex. So I want to consider this as a chain complex where this is degree 0, this is degree 1, 2, 3, and so on. And it will be an exact chain complex because it's a long exact sequence. Okay, so this is C0, C1, and so forth. Exact, just to recall this, exact meant that the homology of C star vanishes in all degrees. And now we remember that in the proof of the Euler-Poincare formula, let me go back, we had a statement here where all the topology was already gone. It all boiled down to proving that equality star, and the proof of that equality only involved chain complexes of a abelian group, as I emphasized. So we can use that also and apply it to this exact chain complex that we have as a result of the Meyer-Vietoris long exact sequence. So apply star to it. Yeah, what is the result? The result is that the alternating sum of the homologies, or the ranks, I should say, the ranks of the homologies is the alternating sum of the ranks of the groups, but the homologies are all 0. So there is a 0 here. And this is alternating sum of the ranks of the groups CP. So let us spell out, at least for P equals 0, or maybe for the first 3 or so degrees, what this means. So this is C0 was just H0. And then minus the rank of H0x plus H0y. That's of course just the sum of the ranks plus the rank of H0a, and then so on and so forth, minus the rank of this plus the rank of the sum of H1x and H1y. And you see where this is going. What you get is the Euler characteristic of the total space C minus the sum of the Euler characteristic of x and y, and then plus the Euler characteristic of y, and that sum is 0. This is what we've shown. This shows the additivity statement. First of all, the Euler characteristic of the circle, that's something that you compute from the easiest CW structure. There's 1 1 cell and there's 1 0 cell. So 1 minus 1, this is 0. For the torus, you could either employ the product formula to see that it's 0, or again use the standard CW complex structure that we have. If you have, let's say, surface of genus 2, then of course you could look at the CW structure that we introduced for any surface of arbitrary genus. But let's play around with the additivity. Just to see this in action, we can view this as a push out. of two tori with a hole. So the additivity then says this is 2 times this piece minus, they're glued along the circle here, so minus the Euler characteristic of S1, which is 0. Now, if you have a torus and you drill a hole into it, then you see from the standard identification as a edges in a square that this is homotopy equivalent to S1 wedge S1. And by homotopy invariance, this is this. Minus 0, you can forget. And then additivity again, a wedge is also push out. It's 2 times the Euler characteristic of the circle minus the Euler characteristic of a point, which is 1, so this is minus 2. In general, without the additivity formula, just from the CW structure that we discussed on surfaces of arbitrary genus, we have the following. So let me draw this picture. We have a genus G surface, meaning that we have G many holes, and then the Euler characteristic is 2 minus 2G. In particular, starting with that surface, it is negative.
And the formula also holds for G equals 0. Euler characteristic of the two-sphere is 2, which is the Euler formula with which we started.
So I want to stop with a beautiful formula without proof called the Gauss-Bonnet formula. That connects the Euler characteristic of a surface, so a topological invariant, with a geometric information. The Gauss-Bonnet formula says that this Euler characteristic is the same as the integral over the surface, so let's call the surface maybe Cg, sigma G. It's the same as the integral of the Gaussian curvature integrated over the surface. So this formula only makes sense if you endow the genus G surface with a metric, and it says that for any Riemannian metric that you put on this surface, there is this connection between the Euler characteristic and the curvature, and therefore geometric information.